local Euclideanness. So locally Euclidean property, how do you show it, right? So the point is, so here are a few things. So what we want to look at is RPN, right? This is the object, and which is nothing but Rn plus 1 minus the origin, and you have this quotient, and where x0, x1, xn is identified with y0, y0, y1, yn, if there exists a t from r minus the origin such that xj equal to, while yj equal to t xj, as I said, yj equal to t xj, which is equivalent saying that xj equal to t yj for all j equal to 0 to n. All right, so this a coordinate in RPN can be written as the bracket, third bracket, x0, x1. Did I write the notation correctly? Just a minute. Let me check this. This is, yeah, x0, x1 up to xn. All right. So this is, and which is, this is called the homogeneous coordinates. Homogeneous coordinates. So I mean, you multiply with t, it doesn't matter. So if you want to find the functions, let's say continuous function on RPN. So what will be a continuous function on RPN? Can you give an example? A continuous function from RPN to R. Can you give an example?
Norm function.
Norm function. Well, yeah, norm function. That's true. Yeah. You find a lot of other things. So you look at homogeneous polynomials. Each of the homogeneous polynomials will give you a function, continuous function on RPN. Okay, so anyway, that is not our concern at this point. Our concern is to look at an open set. For every point, we want to find an open set which will be homeomorphic to some Rn. All right. So you defined uj as collection of all this x dot, x1, xn in RPN such that xj is not equal to 0. All right. So for j from 0 to n, right? So first thing, note that RPN is covered by this uj, right? Is this clear? Because you see, this any point x0, x1, xn belongs to Rn minus 1, Rn plus 1 minus 0. So not all of them are 0. So one of them must be non-zero. So one of them must be non-zero. And choose which one is non-zero and put it in that, right? And the image of that would give you this uj, right? So you look at pi inverse of uj. So to show that, so here, so this I leave you to show that Rn minus 1, Rn plus 1 minus the origin is contained in j equal to 0 to n pi inverse uj, right? Once you have this, then you're done. So this is what you need to show. And this is pretty clear. So any point in Rn plus 1 minus the origin, you will find one of them, one of xj is non-zero. And look at that, u inverse of pi inverse of those uj where that part, that coordinate is, that jth coordinate is non-zero. All right? And it will belong to this pi inverse of uj. All right. Now define a map. Define map phi j from uj to Rn by x0, x1, xn goes to x0 by xj, x1 by xj, xn by xj. All right. So this you define the phi j. First of all, is it continuous? Is it continuous? Yeah, is it continuous? Is phi j continuous? Come on, give any kind of answer.
Yes, sir.
Why?
Because I mean, the original phi j. This phi j is an induced map from from the original continuous function from Rn plus 1 minus 0 to Rn, and there it is just like all the components are rational functions, because there will have tx naught by txj, so t will all get cut and each components will be rational functions, and xj is not 0, so they are continuous. So we are done.
Right. So here you invoke following exercise. Suppose pi from S to S by quotient. This is a quotient map. Then a function f from this quotient space to some topological space, let's say x, is continuous if and only if the composition. So you have S is quotient, this is F, this one. f composed by is continuous. All right. So use this exercise and show that phi j compose pi from pi inverse uj to Rn is continuous. Right? Yeah. Any question here? Any question if you have? So yeah, so now the point is what is the inverse, right? You want to know this is of course this is a map, this is continuous. So answer is yes, it is. Now whether this is invertible, yeah, what will be the inverse of this? What will be the inverse of this? This one. Okay, so let's look at the map. Let us look at the map Vj again. So which is uj for to Rn defined by x0, x1, xn to x0 by xj, x1 by xj, xn by xj. Well, I missed one point, right? So here it is. So this definition of this. See, you have, I mean, you should have pointed out, right? How many coordinates are there?
Sir, we should omit xj by xj.
Yeah, we should have omit that one. So let's omit it. So x0 by xj, x1 by xj, xj minus 1 by xj, xj plus 1 by xj, xn by xj. All right. So this xj by xj, which gives you 1, which is omitted. Now this belongs to Rn. This point belongs to Rn. Right? And you see, if you multiply with t to every one of this here, so this one, of course, this one would come from a map from you see here, from a map of this Rn minus Rn plus 1 minus 0, which is in this case open subset in Rn plus 1 minus the origin pi inverse of uj, because if you multiply with t, with this every member of every coordinate here, if you multiply t, it will go to the same image, right? If you multiply t here, t1, t here, everywhere, so this t by t, it could get cancelled. So it's perfectly well defined map. All right. So this was so here x0, x1, xn goes to x0 by xj, x1 by xj, xj minus 1 by xj, xj plus 1 by xj, xn by xj, right? Now the claim is pj is 1 1. So is it true that pj is 1 1?
Sir, if we just add one xj component in middle and call it a equivalence class with one in the middle, so all the right side components will be the same. Just put one in the xj component.
Right. So this is clear actually. So the point is, what you are saying, this is the following: y naught or y1, y2, y1, y2, yn inside Rn maps to y1, yj minus 1, 1, yj, yn, this one, and now we put an equivalence class instead of this. Uj. So call this psi j. So psi j is phi j inverse. All right. All right. It's clear. So check. So this is for you to check that psi j is phi j inverse, and that is what it said. This is the fact. So psi j and psi j is also continuous. Psi j is also continuous. So therefore phi j is a homeomorphism for all j 0 to n. All right. Now once you have a homeomorphism, so we get a collection, right? So the following uj comma phi j from 0, 1 to n, this is a collection of charts, right? This is a collection of charts in RPN. So here we proved actually, so this implies, here we proved this RPN is locally Euclidean. Because any point you take, it will belong to some uj, and that uj is homeomorphic to Rn. So hence it is locally Euclidean. Now here we have given, so once we have homeomorphism, open set combined with that homeomorphism, that gives a chart. Now you look at collection of charts. Now question is this atlas, right? So question is this collection F an atlas for RPN? So what do you think? Is it true? Yeah. So what do you think?
Yes, sir.
Okay. Right. This is very easy now. So the point is, you look at, let's say U0. Let's calculate with U0 and U1. You can do it with UJ and UK easily, analogously. So U0 is collection of all x naught xn such that in RPN such that x naught is non-zero, and U1 in RPN such that x1 is non-zero, right? So here you have, let's say this is U0 and this is U1, and you have map P1, right? It maps x naught xn to where? To x1 by x naught xn by x naught, right? X naught by x naught gets outside, right? That is one. And here this is p naught, right? This is p naught, and this is phi1, and it maps to, let's say, y naught yn goes to y naught by y1, y2 by y1, yn by y1, right? This is the map phi1. So now we want to do this composition, right? So which is phi1 compose phi naught inverse. So what is it? Yeah, what is it? How do you see it?
So first multiply by x naught.
Yes. Let us see. Just a minute. Okay.
So first we just add 1 in the first position.
Yeah. Right. That's what you need to do. So yeah, let's go back to this. So you want to go from here, right? So which is this side, it is Rn. This side is Rn, right? So phi1 compose phi naught inverse is from Rn to Rn, right? Now you want to look at phi1 compose phi naught inverse, let's say T1, T2, Tn, right? Or yeah, R is the correct one, we put it. R1, R2, Rn. I made again this superscript to subscript. Yeah, it looks like I'm more habituated to with the subscript than superscript. So what is this? You first phi naught inverse gives you, look at this one. This is the map. This is the map. This is the inverse map, right? So it's putting 1 at the jth place. So putting 1 in the first place here. So putting 1, then R1, Rn. And then at one place, you remove one place. So whatever is there, so R1, you divide that by R1, divide everything by R1. So this is 1 over R1, R2 by R1, Rn by R1, right? Which is C infinity because R1 is not equal to 0. Why R1 is not equal to 0? Because you are looking at in the intersection, right? So now it is not of course not whole of Rn actually. So here I made a little mistake here. So this is phi 1 compose phi naught inverse is map phi naught u naught intersection u1 to phi 1 u naught intersection u1. Right? In the intersection, you are not looking at the whole image, otherwise you cannot divide by R1 because R1 might be 0 in the image of U0, but you are looking at image of U1 also, right? And U1 gives the first that the 1th position is non-zero, and that's why you could define. So this is C infinity. C infinity, where C infinity on phi naught u1 intersection u naught intersection u1 because R1 is non-zero. All right. Now, so similarly, we can show phi naught compose phi 1 inverse from phi 1 u naught intersection u1 to phi naught u naught intersection u1 is C infinity, right? And this exercise is routine to check, but just I want you to do this hands-on computation. There is nothing else. So this Pj compose Pk inverse from Pk Uk intersection Uj to phi j Uk intersection Uj is C infinity. All right. So this gives F is an atlas on RPN. Right? Now those who are interested, so once this is an atlas, right? So this gives you RPN is a smooth manifold of dimension n. So RPN is smooth manifold of dimension n, and this is a nice manifold. It will keep on coming again and again. So next is few comments. So few remarks. One can look at Cn plus 1 minus 0 with the equivalence relation Z0, Z1, Zn, W, W1, Wn if there exists lambda in C star C minus the origin such that Zj equal to lambda Wj for all j 0 to 1. Then Cn plus 1 minus origin quotiented with this, which is actually Cpn, is a smooth manifold of dimension 2n. Well, it is actually, so the next comment is those who are, for those who are interested and are interested in complex analysis course also. So it is in fact a complex manifold of dimension n. So complex dimension n. But anyway, that I'm not going to go into this the explanation of this line because that's not for everybody. You can, I mean, those who are interested can come to my office and ask. And second thing is, so instead of lines in Rn plus 1, one can look at collection of all two-dimensional subspaces in Rn, right? So this is let's say G2n, you denote collection of all two real dimensional subspace in Rn. Show that G2n forms a smooth manifold. Oh, there is this place, yeah. So an exercise, show that Sn quotiented with this as before is homeomorphic to Rpn. Hence, Rpn is compact. Right? Any question here? So in the remark 2, so actually on Friday I would like some of you to volunteer for a proof for this remark 2, and more generally the exercise in this book by 2. So exercise 7.8. So those who are interested can volunteer and present that. That is a very interesting object. So this is called Grassmannian, 2 Grassmannian. So Grassmannian is actually all several k-dimensional subspace in Rn you can take, and you will get a smooth manifold structure. there. So quotient of some space of matrices you can get. So this important is this exercise 7.8 of the book. So here, I mean, those who are interested, I can volunteer the proof. Well, not single person. I would like the whole class to collaborate on this and present. There are several questions, several things to present here in the problem 7.8. Okay, in page 82. And on Friday morning, I'd like some of you to present. Okay, so any question?